Hello everyone, my name is Yao Deng. I will present this paper, BMT, Behavior-Driven Development-Based Metamorphic Testing for Autonomous Driving Models. At first, I will introduce the background and the motivation of this paper. Then, I will describe details of proposed testing framework. Finally, I will demonstrate the experiment and the results. Nowadays, deep neural networks are widely used in autonomous driving models for speed and steering angle predictions based on driving images. Some parallel work proposed to use metamorphic testing to evaluate driving models. However, they only focused on equality-based metamorphic relations, where models on follow-up images should produce the same or similar outputs as predictions on original images. However, such metamorphic relations cannot express complex driving behaviors in the real-world setting. For example, traffic rules regulate many conditions where the vehicle should decelerate when meeting pedestrians or traffic signs. Now, no techniques leverage such driving behaviors to generate input images and check the problems of driving models. In this paper, we propose a declarative metamorphic testing approach called BMT, which enables domain actors to specify custom behaviors using a behavior-driven development-based domain-specific language. Then, corresponding metamorphic relations are created, and meaningful test cases are generated to evaluate autonomous driving models. As the figure shows, BMT contains three components: a MR generator, a metamorphic test generator, and a MR evaluator. Initially, a domain expert expresses expected driving behaviors in cucumber-like syntax. Given these behaviors, the BDD parser extracts key elements such as transformation required, and uses such information to build a corresponding MR. Once the MR is created, these key elements will then be passed to the metamorphic test generator, which has an extensible toolkit to implement various transformations required by the behaviors. The transformation engine in the toolkit can manipulate the original input into the follow-up transformed input. In the metamorphic evaluator, the original input and the transformed input are both fed to the autonomous driving model under test, and the model then produces predictions. The evaluator will compare each output pair of predictions on the original input and the modified input, detect faulty pairs that violate the underlying MR. Such violations show potential safety issues of driving models under test. The top left box shows the behavioral template of BMT, with the cucumber-like syntax, 5 key elements including transformation, object, location, precondition, and expected change should be provided. The bottom left box shows the proposed 5 behaviors in this paper. For example, for behavior 1, the transformation is adding, object is the vehicle, location is in the front, precondition is the input image meets the requirement to add a vehicle in the front of the ego vehicle, and the expected change is the speed should decrease in T1% to T2%. Such a behavior can be used to create MR like the formula shows, where F represents the model and outputs the prediction result based on input data. Function G represents the generator to implement required transformation operation on the source test case based on transformation object O and location L. Data 1% and data 2% are bounds of the range specified in expected change. To implement transformations required in behaviors, we integrated 3 transformation engines: Pix2Pix HD, Unit, and OpenCV. Pix2Pix HD and Unit are 2 powerful generative adversary networks for image generation. OpenCV is a famous library for image processing. Other transformation engines can also be integrated to BMT. Now I will introduce the experiment settings and the results. In the experiment, we trained 3 driving models with different network architecture, Epoch, VGG16, and RaceNet 101 on the Seascape dataset. The threshold of expected change of each proposed behavior was set as the slide shows. We mainly studied 2 questions. The first research question is, how well these scenes generated from behavior-based MRs can reveal erroneous model predictions? We generated test cases and MRs of 5 proposed behaviors to test 3 dry models. BMT then found violations of MRs for 3 dry models. The second research question is how meaningful the reviewed erroneous predictions are as rated by experimented human judges. For this question, we provided detected violations in research question 1 to 6 human raters. They then rated each violation in a 7-point Likert scale, where 1 means a detected fault is indeed a real violation, where 7 means the detected fault is absolutely not a violation. The figure shows examples of generated transformed images of 5 behaviors. The table shows detected violations on test scenarios generated based on 5 behaviors. For 3 models, the violation ratios of 5 behaviors are over 80%. For behavior 3 and 4 on epoch model, the violation ratios achieve 100%. The result means BMT can detect a significant number of erroneous predictions of driving models. The box plot shows the ratings of 6 raters on 3 models. Some key information can be extracted from the figure and the experiment result. The average rating for Epoch, VGG16, and Recent 101 is 2.7, 2.7, and 2.8 respectively. The average rating for the 5 behaviors is 2.9, 2.2, 2.3, 3.0, and 2.6 respectively. This result means violations detected by BMT looks like real violations of traffic behaviors. In the future, we will improve BMT from 3 perspectives. We will extend the domain-specific language to more precisely describe testing scenarios. We will also extend to create scenarios of more complicated behaviors. Finally, we will develop a prototype for domain experts to easily create test scenarios and test driving models. That's all. Thank you. Do you have any questions?
Through your paper, I noticed that your paper has say 5 basic types of behavior, right? 5 basic types of behavior, like adding an object in front of a vehicle, or like change from daylight to evening, or change from a sunny day to a rainy day. Now, I'm pretty sure that there are other conditions that may affect the safety of the vehicles. So my first question is, have you actually considered other ML besides these 5 basic behavior?
Yes, we are considering many and other more complicated scenarios we may meet in driving. For example, for the maybe line changing or merging or merging or parking like this. We now are working on these behaviors and to design more metamorphic relations. But because now basically we just implement the 5 basic metamorphic behaviors. But we consider more.
Because I got a feeling that the work in that paper can be extended by performing more experiment or case study using a more comprehensive set of MR to represent different driving condition or scenarios.
Yes, and now we also focus on the image-based testing, so we can also extend it to maybe LiDAR data or other kind of data to define more MR to test autonomous driving systems.
Now, my second question is, if you remember, in your paper, particularly in the introduction session, you mentioned that a recent road accident involved Tesla autopilot system, and that eventually, affect human life. Now, my question is, have you actually used your methodology to define an MR that you think will cover that scenario?
I see.
So my question is, have you actually analyzed the root problem, the root reason for that accident, and then define an MR that you think can detect the fault of the autopilot system to prevent this accident from happening in the future?
We didn't analyze this accident, but we researched some other literature, and they gave some explanations. They said the Tesla caused this accident because the vehicle misclassified the truck as other objects, and the car didn't stop, just kept running. So actually, I think such accident is similar as our some behavior, such as a person suddenly appear in the front. So I think they may be similar, but maybe we can design more specific MR to detect such.
Because I think if you can actually find out the reason, the actual reason contributing to this accident, and then able to demonstrate through your model, you can define an appropriate MR to prevent this problem from happening. So that will create a much better impression to the general audience, because now you can show that your model or your methodologies is able to define MR that catch something actually happened in the past.
Yeah, this is a very good suggestion, and we will consider this, and we will do some experiments about on this. Yes, thank you very much. Yeah.
But other than that, I think your models, your approach, the BMT, is pretty good.
Thank you.
So may I ask any other question the audience want to ask the presenter? Now it seems no. Then we are now 5 minutes ahead of the next paper presentation. Maybe we can take a rest, okay? And I'll see you in the second paper presentation. Okay, thank you.
Thank you.
Thank you.